Since I'm gone today, I want to make sure that you have the opportunity to get a explanation for and what the expectation for an answer would be if given questions similar to these that we practiced in class but didn't have time to finish. So I'm going to start off at the very beginning for all of them so that you can hear it again for some or maybe for the first time. So which would have the largest radius, nitrogen or selenium? Explain. Well, if we look at where nitrogen is located on the periodic table and we look at where selenium is located, we see that selenium is in the fourth period and nitrogen is in the second period. That means selenium has more energy levels. So if you were going to answer this question, we would say the largest radius is going to be with selenium, and the primary reason for that is because it has more energy levels. Now, a secondary reason to this would also be that there is going to be more repulsion between the core electrons and the valence electrons in selenium than in nitrogen. But the primary reason is that selenium has more energy levels, and the higher the number of energy levels, the further electrons are away from the nucleus. For the next one, which would have the largest radius, magnesium or sulfur, we're going to look at, again, where they located at. Magnesium is located in the third period, as well as sulfur being located in the third period. So the difference here, the primary difference, is that sulfur is going to have more protons. Yes, it has more electrons, but the key here is more protons. So in answering the question, which would have the largest radius, magnesium is actually going to have the larger radius because sulfur has more protons, meaning there's going to be a greater attraction, more so than the added repulsions from electrons. And that added protons and increased attraction causes atoms to get smaller as you move from left to right across the periodic table. So again, in summary, sulfur has more protons, greater attraction. That greater attraction makes the atoms smaller going to the right. In the case of the ionization energy for chlorine and tin, what we're going to be able to do is also now incorporate the size that we were talking about in the previous two questions. So chlorine and tin, again, let's take a look at where they're at. Chlorine is located in the third period. Tin is located in the fifth period. So we have a fairly significant difference in the size, with tin being larger than the chlorine due to its more energy levels. For that reason, then we can say that the smallest ionization energy is going to be for the chlorine because the smallest ionization energy is going to be for the tin because the tin is going to have electrons further away from the nucleus. That reduces the attraction in comparison to the chlorine. Tin also has more electrons between the core and the valence, causing more repulsion. But the primary reason why tin is going to have the smaller ionization energy is because the electrons are further away from the nucleus. In the next question, we're looking at lithium and carbon. If we look at where they're located at, they are located in the same period. So the second period, lithium, second energy level. And what we're going to see here is that the smallest ionization energy is going to be affected by the protons and the size again. Only this time around, it's going to be the lithium because lithium has the least number of protons attracting the electrons in the same energy level. Carbon is going to be smaller. It's smaller, it has more protons. It's going to have a greater attraction for the electrons than what the lithium is. In the next question, which would have the larger ionization energy for electrons in the 2p sublevel, gallium or vanadium? Explain. In this case, again, we're going to go look at where they're at. We have gallium in the third period. We have gallium in the fourth period. We also have vanadium in the fourth period. So both of them are going to have electrons in the 2p. Now the 2p electrons are represented by this row up here. So both of them are going to have electrons in the 2p sublevel. Now the difference is going to be, in this case, what's different about gallium or vanadium? Now we're going to make the assumption that the 2p sublevel for gallium and vanadium are going to be relatively the same distance away from the nucleus. In reality, and this will be kind of explained by what you're going to hear next, the gallium will have, the gallium's 2p sublevel will be a little bit closer than what vanadium's will. And here's why. In gallium, you have more protons than you do vanadium. That increased number of protons is going to increase the attraction for the electrons in the 2p sublevel. Now, the 2p sublevel, if it's relatively the same distance away from the nucleus in gallium and vanadium, that alone, the increased number of protons, will cause it a larger ionization energy in gallium because it has a stronger attraction due to simply having more protons. But in addition, the gallium's 2p sublevel will actually be a little closer than what vanadium's will. So not only is it an increased number of protons, it's also a decrease in the size between the nucleus and the 2p electrons, increasing that ionization energy. Now, the last question, give an explanation for the decrease in ionization energy between phosphorus and sulfur. If you go look at a data table, you will see that there is a slight decrease in ionization energy between phosphorus and sulfur. Now, this goes against the trend that we usually see for going from left to right across the periodic table, which we should see that there's going to be an increase in ionization energy as we move from left to right, but there's actually a slight decrease. Now, if you were to write out the orbital notation for phosphorus, you would see that in the 3p sublevel, you will have 3 electrons, and if you're doing the orbital notation, that means that each orbital would only have 1 electron. If you do the orbital notation for sulfur, sulfur is going to have 4 electrons in that p sublevel, and that's going to require a pair of electrons in one of the orbitals. That pair of electrons increases the repulsion between the electrons and actually causes the ionization energy to drop a little bit between phosphorus and sulfur. Now, this question is kind of a stretch, but it gets to the heart of what we want to look at when you're looking at these trends. We look at where the placement is on the periodic table, and for small little variations, you can look at details of how the electrons are located in the atom and use that to help give some explanations, like with phosphorus and sulfur. Hopefully you understand these explanations. They are explanations we've been using for the most part throughout the unit. They do go to the heart of the equation, Coulomb's equation, which is that V equals K Q1 Q2 divided by D. And that equation is important for us to be able to look at the relationships between things and make some prediction based on those values and how they're changing.